Hey everyone, this is Professor Ross, and in this video we'll be talking about comparing two proportions with a simulation-based approach. So we're in this scenario where we have two categorical variables, and we'd like to do some inference, and we'll use a simulation-based approach for that. Let's take a look at a few notes here. Our key learning objective for this unit, and especially here in this uh, video, is thinking about using the logic of statistical decision making. So we're thinking about how we can do this statistical decision making of inferential procedures in this scenario where we have two categorical variables. So inference with two proportions. Two-way tables help us examine whether there's an association between two categorical variables. If we have a scenario where we've got two categorical variables and we want to explore the data, we can look at a two-way table and think about, are those two variables associated? If we only have a sample from a population or an infinite process, we're going to need to use inference to try to extend our conclusions beyond just a sample. That's what statistical inference is. Take results from a sample, try to make conclusions about a bigger population or process. We're still going to use that same overall 6-step approach. And specifically, if we're going to do a simulation-based approach, we're still going to use the 3S strategy to assess strength of evidence. There'll be a few differences because of the different scenario, but we'll find out that a lot of things turn out to be similar to what we did before when we took a simulation-based approach with the 3S strategy. So here's the example we'd like to talk about: swimming with dolphins. Researchers recruited 30 subjects with mild to moderate depression and had them stop medication for a study. They randomly assigned these 30 subjects to either swim and snorkel for 1 hour with no dolphins, or swim and snorkel for an hour with dolphins. So they took their 30, randomly assigned them to one of the two groups, either with dolphins or without, and then at the end of 2 weeks assessed for substantial improvement regarding their depression. So we've got two categorical variables. One of the categorical variables is our explanatory variable, and it's whether they were with dolphins or not. Note that they try to keep as much the same as they could besides this one specific thing, the dolphins, so they still had their control group swimming and snorkeling for an hour. So that's explanatory variable, and it's categorical. We've got the two categories, with dolphins or without. Our response variable is also a categorical variable. They decided yes or no, they were seeing substantial improvement for depression. So yes, improvement, substantial improvement, or no, not substantial improvement. So let's talk about our hypotheses in an inferential scenario. They just did this with 30 participants. They'd like to hopefully draw conclusions beyond those 30 and maybe extend that to a larger population of people with mild to moderate depression. One hypothesis is that is what we'll call the null hypothesis, and that one's going to be that there's no association between swimming with dolphins and relief from the depression. So the null hypothesis for all of this unit and pretty much the rest of what we look at is always going to be that there's no connection, no association between our two variables. And here we can phrase that this way: the probability of showing substantial improvement after swimming with dolphins is the same as the probability of showing substantial improvement after swimming without dolphins. In other words, it doesn't matter if you're swimming with dolphins or swimming without dolphins, we're going to see the same kind of results. There's no connection between the dolphins and the probability of substantial improvement. We can symbolize that, and we're going to have two different formats, but I'll tell you about the one I prefer and the one we'll tend to look at. So, but first, let's take a look. So, HO, the null hypothesis is pi dolphins. What's pi stand for? Don't forget, pi is our proportion of success out in the population. Proportion of success. And here, success we're going to naturally define as substantial improvement. So what's the dolphins mean? Well, this is the group that swam with the dolphins. So we're talking about the proportion of success for the group that swam with the dolphins equals, once again, pi, the proportion of success that did not swim with the dolphins, swam without the dolphins, I should say. Now, don't forget, this is proportion of success in the population. So what we're talking about is making a claim about what would happen out there amongst all people with mild to moderate depression, assuming we feel it's fair to extend our results to that population. The null hypothesis says out there amongst all people with mild to moderate depression, it doesn't matter if you swim with dolphins or you swim without dolphins, we'll see the same proportion of improvement, substantial improvement. Another way to write that mathematically is to write the proportion of success for the dolphins group minus the proportion of success for the control group turns out to be 0. Now, mathematically, you can hopefully see why this would make sense, that it's saying the same thing as our other equation. If I take two things and they turn out to be equal, the same number, and I subtract them, let's say this is 0.6 and this is 0.6. If they turn out to be equal and I subtract them, I should get 0. So that's the same thing as what we said over here, if this equals this. What's the advantage of doing it this way? This mirrors what we often are interested in as far as a statistic for our study. We looked at this in the last video, the difference in conditional proportions. So I like this format because it's mirroring what we are interested in the study. We calculate the proportion of success in each group and subtract it. That's our statistic. And that looks like p hat dolphins minus p hat control. And that's the statistic we're going to examine. And that mirrors this format here, pi dolphins minus pi control. Pi, of course, means this is about the whole population. P hat means that's about our sample. So I like the fact that it mirrors that. And so this is the format that I will tend to use for the rest of the course. So that's the null hypothesis, that the proportion of success in both groups turns out to be the same. How about the alternative hypothesis? Well, the researchers clearly think that swimming with dolphins is going to do something that just swimming without any dolphins won't be able to do. So the alternative they're believing is that the probability of showing substantial improvement after swimming with dolphins is greater than the probability of showing substantial improvement after swimming without dolphins. So once again, we've got pi dolphins for all the people with mild to moderate depression. If they got to swim with dolphins, the proportion of substantial improvement would be greater than the proportion of improvement for folks who got to swim but didn't have dolphins. Once again, I'm going to prefer this format, and for the same reason, it mirrors this statistic that we're interested in looking at. So pi dolphins minus pi control is greater than 0. Now, mathematically, how does that work? Well, you might remember back to your algebra days, if you just simply subtract this from both sides, pi control, subtract that from both sides of the inequality, you'd end up with this. So that's one way to think about it. But also, we can tend to think about it this way. If you're subtracting two things, and when you do that subtraction, you get a number that's greater than 0. In other words, a positive answer. Which one must have been the bigger thing? It must have been the first number that was bigger minus smaller would give us a positive number. And then, so that's saying the same thing as this. This is greater than that. Okay, so those are our two hypotheses, and that's what we're going to use for our hypothesis test. Let's take a look at how that's going to work. So here's our data. You can see we've got a two-way table, and we should calculate some values from this. So I encourage you to pause the video for a moment take a look at the data in the two-way table and try calculating the conditional proportions, the difference between conditional proportions, and the relative risk. Okay, so what are the conditional proportions? Well, we've got our two categories in our explanatory variable, swimming with dolphins or swimming without dolphins. And conditional proportions are simply the proportion of success in each of those groups. So p hat for my dolphins is how many successes I saw. Here, 10 showed substantial improvement out of the 15 total. That's a proportion of approximately 0.667. So that's one conditional proportion. The other one is the proportion of success for my control group, where there were no dolphins. And here I saw 3 out of 15. And that is a much smaller proportion of success. That's 0.215. So I've got my two conditional proportions. And it's already pretty clear that things were going better when people were swimming with the dolphins. We got a lot higher proportion of success than without. What is the difference between those two? Well, we simply subtract them, 0.667 minus zero point 0.2, and that would give us 0.467, almost 50% more success with dolphins than without. That's a pretty big difference. How about the relative risk? Proportion of success with the dolphins, 0.667, divided by the proportion in control. And that turns out to be about 3 1/3. And what's that telling us? You are 3 times more likely to see substantial improvement when swimming with dolphins than swimming without dolphins in our sample. That's huge, 3 times as likely. Uh, if I had mild to moderate depression, I had the choice and I saw this, I would say, boy, let me swim with some dolphins, right? I'm 3 times more likely to see some improvement. So we can see from our statistics already that it certainly seems like which group you ended up in made a difference in the response, whether you saw improvement or not. So it seems like there is an association between our two variables here. But once again, this is just for our sample. Can we really make that kind of conclusion for the broader population of folks with mild to moderate depression? In order to do that, we have to do inference, and we can use a 3S approach to doing inference. So we have a choice of statistics. We can actually either look at difference in proportions or we could look at relative risk. Much of the time for this course, we'll look at difference in proportions, but you can choose relative risk and the results will turn out the same if that one makes more sense to you. Our 3 S's. Number one, we simulate. So first we're going to simulate randomly assigning our outcomes, improvement or not, to the two groups of the explanatory variable, dolphins or not, and check the randomly produced statistic. We need to think about this idea a little bit. How does this simulate what's going on? First, quick note, we're not going to change the number of successes or failures. We're simply going to change which groups they end up in. So I'm going to jump back to the two-way table to kind of talk through this idea here. Essentially, what we are saying with this simulation approach is we are saying that we're assuming the null hypothesis that it doesn't matter if you swim with dolphins or not. That's not going to change whether you showed improvement or not. In other words, these 13 total people, it doesn't really matter which group they end up in. They're the ones that were going to show substantial improvement no matter what happened to them. So somehow we got to take these 13 people and randomly divvy them up between my two groups, dolphins and control group. And so I could just do that. I could just take the 13 and I could say, I'll flip a coin. If the coin comes up heads, you're in the dolphins group. If the coin comes up tails, you're in the control group, and split them up that way. Similar kind of story for this 17. Those are the ones that were not going to show improvement no matter which group they ended up in. And so we could similarly split them up. An easy way to think about this was to think about like little cards. If I had 13 green cards, green showing they're the improvers, and 17 red cards. They're the ones that weren't going to improve. And I put them in a big stack of 30 and I just shuffle up all my cards. And then I deal out 15 for my Dolphins group and 15 for my control group. And then I can simply see how many successes showed up here in my Dolphins group and how many in my control group. What does that random shuffling do for us? Well, it simulates this null hypothesis that it doesn't matter which group you end up in, that's not connected to showing substantial improvement or not. So we're simulating that aspect. Then what do? We do the same calculation. We calculate conditional proportions, and let's just talk about difference. We'll focus on the difference in conditional proportions, and we see what it is from our shuffled up simulated one. And we do that a whole bunch of times, 1,000 or even 10,000 times. And we ask ourselves, what kinds of results do we tend to see? And in the end, are those results something like what we saw here? Or was our actual result nothing at all like what we would predict if the null hypothesis were the truth? So after we've done our simulation, what we do then is check that strength of evidence. We see how often a result like our statistic from our sample would occur, or more extreme, if there were no association between the variables. In other words, if they were just randomly assigned to the outcomes. Guess what that is? Does that sound familiar? That is a p-value. So we're going to calculate a p-value just like we had before, and guess what? It's the same interpretation as before. Let's check out the applet and try this out. I'm going to go ahead and pop over to the applet. We are now talking about a simulation-based approach with 3 S's and now 2 proportions, not a single proportion anymore, but 2. Now you can see by default, this applet happens to have my dolphin swimming data in here, so I don't have to type it in. But if I needed to, I could change these values to match whatever two-way table I have. Make sure you hit use table if you type in different data. You can also see a segmented bar graph here, and we can see a lot higher proportion of success in group A swimming with the dolphins than not. Now, in order to do my simulate, one other thing. We can define success or failure. We can pay attention to whichever one we want. By default, success, the top row, is what we pay attention to. And we can also switch around which ways we subtract it. So we can do group A minus B or B minus A. You can see that it calculates the difference in conditional proportions for us, and it gets the same value we saw before, 0.467. If you didn't want to look at the difference, you could change to relative risk. There are also a couple other statistics we could calculate that you might want to explore and find out about, but for now we're focused on difference in proportions. So now how do we simulate shuffling these things up? Here we go. And what they have marked for us here are, I think I had the colors switched around, but they've got 10 plus 3 more blue cards. Blue means those were the people who successfully showed improvement from their depression. Green cards, 5 and 12 more here, those are the people who failed to show successful improvement. Now, the null hypothesis would say, doesn't matter if you're in group A or group B, swimming with dolphins or not. If you're blue, you're blue. If you're green, you're green. Let's shuffle them up and see what happens. So we randomly shuffle them up. We get our 2 groups. Here's the group that swam with dolphins. Here's the group that swam without dolphins. And we can see the proportion of success. And you can see here it's fairly low proportion of success. And here it's a fairly high proportion of success. When I subtract those two, I end up with a negative difference. You can see here negative 0.333. So that might be one typical kind of result we'd see if the null hypothesis were true, no association. I'll shuffle one more. You can see once again, oh, we actually ended up with the exact same difference. If you're trying this out, you're probably seeing some different numbers. If I hit it again here, okay, so now I saw higher success here, a little lower success here, a small positive difference. It shouldn't be surprising to you that we see some positive, some negative, because these are being randomly shuffled around, and they should center around a 0 difference. Now, we want to do this a lot of times and then see what pattern emerges in the long run. you might not be too surprised to see here that it looks like a somewhat normal shaped distribution, and it's centered around a zero difference. In other words, it doesn't matter which group you're in, we're seeing the same proportion of success. What we want to find out is, was our result strange or abnormal? Or was our result something very much like we'd expect if the null hypothesis were true? Our result of positive 0.467, we can put that in here, 0.467. And then I can choose, do I want greater than, less than, or beyond? How do I know which one of these I want? Greater than is shows me everything above, less than shows me everything below, beyond shows me the two tails. Well, the way that I know which one to pick is I want this to match my alternate hypothesis. So here we said the alternative hypothesis is that it'd be greater than, because we expect to see more improvement if you're swimming with the dolphins. And here we have a number in red. That is the p-value. We have a very low p-value. There's only about a 1% chance of seeing a difference as big as 46% in the conditional proportions, or greater than that, if the null is true, that there truly is no difference between the conditional proportions. This is something that's very strong evidence. Well, not quite very strong. We call it strong evidence against the null hypothesis. And we should reject that null hypothesis. Let's jump back and take a quick look. So we found a p-value, and it gave us strong evidence against the null hypothesis. And so we're going to reject the null hypothesis. And so here's the one. This null hypothesis says it doesn't matter which group you're in, same proportion of success. We're rejecting that. So instead, we feel like this is true. This is indicating that this group is greater than that group, that the proportion of success when you swim with dolphins, the proportion of substantial improvement when you swim with dolphins, is indeed higher than if you swim without dolphins. So that's how we take a p-value and interpret what it's telling us. Let's think about a few other things for our conclusion here. Oh, excuse me, for estimation. We can calculate a confidence interval in the same way we have before. Now, what's the confidence interval for? We just said we expect to see more improvement when you swim with dolphins. The natural follow-up is, how much more? Are we going to see a lot more improvement, a lot more substantial improvement with dolphins than not? The confidence interval will tell us how much more improvement we can expect. With the simulation, we can use the 2SD approach. So we take our statistic, that was our difference in conditional proportions, 0.467, and we multiply, or we add and subtract the margin of error, the 2SD, 2 times the standard deviation of the null distribution. So we can find that standard deviation if we look back at the applet here, and I think I'm actually in the way. Here it is, standard deviation of the null distribution, 0.184. 0.184. So I'm going to jump back and put that in there for our calculation. So it's going to be our statistic, 0.467, plus or minus 2 times the 0.184. So 2 times 0.184 is going to be, what's that going to be, 0.368. And then I'm going to add and subtract it for my high and low. So let's go ahead and get the high one here, 0.7, 0.8235. And then let's go ahead and subtract it for the low one. Let's see here, 17 minus 8 is 9, 15. Just about 10%. So we've got essentially 10% up to about 83%. Let's interpret that. The base interpretation for every confidence interval turns out to be the same. We believe our parameter falls in there. The key question for us is, what is our parameter here? And that is what we had in the null hypothesis. pi dolphins minus pi control. The difference in success, we believe, out in the population would fall somewhere between these two numbers. In other words, and which one of these two is higher? The dolphins, right? That was more successful. So we believe we'd see somewhere between about 10% all the way up to 83% more success when folks are swimming with dolphins versus swimming with control. Now, the 83% seems like, wow, that's awesome. But we really should focus on the low end and say we should expect to see at least about 10% more success swimming with dolphins. So now we've decided that we would indeed see more success swimming with dolphins. How much more? Well, at least about 10% more substantial improvement. And that helps us gauge how meaningful this is. Are we seeing just a tiny little bit? Are we seeing a lot? About 10%. And whether that would justify the additional expense and cost of trying to go swimming with dolphins, it helps us understand whether that's worth it. So we've decided that it sure looks like things go better when they're swimming with dolphins versus not, and we got a sense of how much better. What type of error are we at risk of? Whenever we reject the null hypothesis, which we did here, it's a type 1 error. How probable is it? Well, if we had an alpha of 0.05, which is what we typically go with, then we're looking at a 5% chance of a type 1 error. So we do have some risk of a false alarm here. There's a small chance that it might not actually be true that dolphins help with substantial improvement. What population can we generalize the results to? This is a tricky one for us to answer here. Should this be all people in the whole world who have mild to moderate depression? That seems a little bit extreme, especially because we have a very little information about these subjects. It just says researchers recruited 30 subjects. It doesn't sound like they used a random approach for getting their sample. And so we have to be very hesitant about who this might actually apply to. The results are promising and might suggest that we should try to do a study where we do a better job of randomly sampling broadly from the population so we can generalize better. Right now here we'd say pretty limited and questionable about who we can generalize results to. Causation, can we say it was swimming with dolphins that actually caused the substantial improvement? And here we can say yes. It was the dolphins that caused it because they did random assignment to the two explanatory groups. So they took their 30 people and they randomly assigned them to either swim with dolphins or not. And that allows us in the end to conclude that the only difference between those two groups, they should be pretty similar in aggregate in every way, except one group with the dolphins, the other group without the dolphins. So yes, it should have been the dolphins that caused the difference we see. Looking back and ahead, how could we improve the study? Probably the biggest thing here would be to do a better job sampling if possible. But that can be really challenging in settings like this where you do need people who have the condition, mild to moderate depression, are willing to go off of medication, are willing to spend time doing your treatment here of swimming with dolphins. So that can be pretty challenging, but that might be a place to focus on improving. All right, that's the simulation-based approach to when we have this scenario of two categorical variables.